Hi, welcome to this part 4 of IPC mechanisms. Let us see from what we have completed, let us continue from there. So, though I mentioned about being conscious about how to use semaphores and making sure that you do not make a mistake of forgetting to call a semaphore, or if what happens if you miss out to call a release semaphore. Now let us document all of them and then see the issues with a semaphore, and then how do we solve it by introducing mutex in the discussion. Okay, that is what is being followed in the OS. So you are supposed to know the difference between semaphores and mutex, and how does this mutex solve the problems that semaphores have. Now, what are the issues or criticisms on semaphores? Semaphores are an elegant low-level synchronization primitive. However, their use is error prone. Okay, why do we say low level synchronization primitive? Because it is done by the OS with the help of the CPU, because any operation that you do with the semaphore has to be atomic, because there shouldn't be any, when I say atomic means you should not have any context switch in the middle of your operation. Then what happens is some process thinks that it has control of the semaphore, or it acquired a semaphore, but whereas some other processes already entered the critical section. It could possibly happen that if the operations on semaphores are not atomic, then you will have an issue. That means anything that is done on the semaphore has to be completed before some other process has a chance to do something on it. So the semaphore variable, though I said that it is implemented in the OS as a in software, but I mentioned also that it is with the help of the CPU. So there are, just to give you a glimpse of what is happening. The issue is basically when you are trying to increment the count, we saw that the count variable has to be read from the memory and then incremented by the CPU and written back, right? This is reading and writing, and this is the ALU operation. These are all three assembly instructions, and I mentioned that in the middle of any of these three instructions, if there is a context switch and some other process gets a chance to access the same count, it is going to get an erroneous or wrong value, or whatever incrementing happening may not be actually getting reflected on this common variable accessed by two different processes or many. Now, I also say that semaphore is also use semaphore or sync semaphore, any semaphore that I have, they are also being implemented in software. That means even this use variable, which is maybe maintained by the kernel, this also has the same issue that normal user like you and me have on the variable access. So how is it prevented that when OS does it, nothing happens? Same, it implements a thing in a semaphore in software, whereas when I try to increment a semaphore or a variable, it is having an issue. The reason is there is an instruction which does this read operation and then some checking of whether it is 1 or 0, and then modifying it and writing it back. Okay, so these are all three different instructions which are normally executed by you and me in a user process, like load instruction, and then we say that increment instruction maybe, and then store instruction. Now when you have these kind of three instructions, and interrupt can happen anywhere in the middle of those instructions, we have an issue that context switch could happen, because timer interrupt itself is a could be possible that the quantum is completed and the timer has interrupted and the process context switch has happened. So because of that, the value which has been read into the CPU is not incremented and stored back immediately, and there is another process coming in the middle. So this should be avoided even if the semaphore is implemented in software by the OS. So there is a test and test and set instruction. That means it will test it or test and clear, whatever it is. Okay, that could be any, you can implement it in any way, but there is an instruction, one single instruction where which is atomically done, reading this value and checking whether it is busy or not, and then making it free and writing it back. Okay, whatever may be the implementation internally. So that operations are all done atomically, or though it is multiple operations, the processor is doing it without any other processor, even if it is a multi-core processor, any other process getting a chance to access that particular variable. Before that, the changes are done and atomically it is protected. So that's how semaphores are implemented in the OS, though it is in software, because it is running in the kernel mode and it has got a permission to execute some special instructions, which also includes one that is used for updating the semaphore and checking the semaphore and updating it. In case if it is free, I will update it and write it back. Okay, so this is just a information that you can have it in, to understand how semaphore is implemented in a processor or by the OS. So it's a low level synchronization primitive which I mentioned that it is happening at the assembly instruction level. If a semaphore is omitted, now I am talking about whether you are forgot to use the semaphore before using the critical section, entering the critical section, then the entire program can collapse. A more structured synchronization primitive is required. So we don't want this kind of wait and signal semaphore function calls where which anybody can be allowed to call it. So erroneously somebody can release a semaphore without even owning it. Similarly, somebody can multiple times try to acquire a same semaphore. Then what happens? Suppose I say that some wait I do, that means I am acquiring a semaphore. Okay, that means I own it. While I own it, I say that I want again the same semaphore. Nobody prevents me from doing it, right? S1 and S1, the same semaphore. Then in what happens is assume that it is a binary semaphore, then you already own it. That means the count was earlier it was free, which was 1. You made it busy by making it 0. Then the same process comes and says I want the same semaphore. Now you cannot get the semaphore which is already owned by you. It is the rule is same. Okay, suppose you lock the house and then you miss you lose the key. You can't say that I am the owner of the house, so please you should open without me using the key, right? You need to have the key to, even if it is your own house. So even if you are owning it, if you ask for it again, it cannot be given because it's only one binary semaphore. So what will happen? This process will get blocked, and who is going to release it? Because this process is having it, is supposed, if it is supposed, if this is what is supposed to release it, then it will never release the semaphore and it is going to be permanently blocked. So repeated calling of the same semaphore also could cause a problem. And then you suppose process P1 is owning it, some wait it has done, okay, and then it is in the critical section. Okay, now process P2, it doesn't own it. I told you that wait and signal are the pair of instruction which you need to use in the critical section. But without even owning it, if you include execute an instruction which is signal, OS is not going to check whether the semaphore you really own it now before you release it. It is not having a permission to check it because semaphore does not have any information about who is the owner of the semaphore. So you can accidentally release it without even owning it. Now what is the issue? The issue is somebody waiting for that semaphore may think that it is free and enter the same critical section. They may even update the same database, while this process which is not even aware that the semaphore which it is owning has been released by somebody else, and one more process is also in parallel with me executing it. Please remember, even though they are operating on the same database, and if this happens to be running on multiple core or the same core, doesn't matter, each process, that other process will not know that the same data is being acted upon, because the semaphore is the only way to know it. It's the entry point. Inside that, every data that you access, you are not going to have a mechanism to say whether am I the only person accessing it or some other process is also accessing along with me. So there is a total collapse of your program and the data can be corrupted. Okay, it's all very time based. It could run without any problem, but that's not guaranteed. So you need this kind of erroneous function for calling the semaphore functions is a problem. So we need a more structured way of implementing the semaphore. So even no high level current concurrent programming language relies entirely on semaphore. So even there are some programming support is there for a semaphore. Synchronized variable, synchronized name is there in Java, which is actually implementing the semaphore. So we'll when you learn about the languages, you will know how the semaphore is used in those kind of scenarios. It is internally the programming language converts them into a semaphore, and it takes the help of OS to implement it or use it. So semaphores are important historically, but are arguably not adequate for real-time domain. So now, what are the problems? Accidental release. I told you that somebody who is not even owning a process releases the semaphore accidentally, either by intent or maybe without any proper intention, but by mistake. Recursive deadlock. I mentioned that also. You own a semaphore and then again call the simulate again on the same semaphore. That means the process who is already owning it ask for the semaphore. If it happens to be a binary semaphore again, you cannot get it again. So another possible problem that you can have with the semaphore is the process deadlock. That means a process is acquired a semaphore successfully and it is in the critical section, but by some chance, maybe it does some illegal access to some data, or it did something wrong, or somebody else, a user or someone has killed the process, like control C signal. Then what happens is the process, after owning the semaphore without releasing it, if it process is killed, who is going to release the semaphore? Nobody. Okay. OS does not have the information now that who is the owner of the semaphore. Somebody has acquired the semaphore. It knows that many processes are waiting for the semaphore, but if it doesn't have any information stored along with the semaphore data structure, the OS will not have a clue of who has acquired it and who has prematurely got into got killed, or it even by mistake it exit without releasing the semaphore. There is a problem where other processes are not going to be getting the semaphore and they are going to be permanently blocked. So these are the problems, and then there is one more priority inversion which is not part of this syllabus. This course we'll cover it later on. Okay, so how do we solve all this? Mutex is the solution. Now Mutex, remember, it's a semaphore and it's a binary semaphore, and on top of it, it solves all the problems that we saw with the semaphore. Okay, it's actually basically a binary semaphore, but it has additional information, and OS solves the problems that semaphores faced by implementing mutex. Now, what is it that? Mutex is similar to the principles of binary semaphore with one significant difference: the principle of ownership. So, all the problems, if you root cause of all the problems that we saw with the semaphore is OS does not know who is the owner of the current semaphore, or not currently who is the owner of the semaphore. And if okay, the problem will be same for even counting semaphore, but it may appear after some time. Okay, so you can assume that if the problem is there in binary semaphore, it could happen in counting semaphore also, but maybe it may be delayed. So issue is the same. Whoever is the owner of the semaphore, if the OS does not know which process is owning it, this could lead into any of this erroneous usage of semaphore could cause a problem for the software. So ownership is a simple concept. You need to, when a process acquires it, it owns a mutex. Okay, now I am going to call this as a mutex because ownership is there. So, and only it can unlock it. Only the owner who owns the mutex can unlock it. Then the accidental release is gone now. Nobody, if the process does not have it does not even acquire the semaphore, it cannot accidentally release it also. Okay. So when a process tries to unlock a mutex, which it does not own, an error condition is raised. So OS is not going to blindly accept signaling the mutex. Signaling the releasing this mutex, because it knows who is the owner and it will check who is the current process which is running. See, always remember that there is in a CPU there is a special register which holds the current process which is being executed on the CPU. So anytime OS system call is done and somebody is trying to release it, it can always go back and check that register content to see which process ID is currently running on the CPU, which is calling this function, and then it can internally check the mutex data structure in the OS. to verify when that mutex was acquired, it keeps that value. Okay, it takes from the CPU and stores it in the mutex database. Well, basically a structure of mutex. And when somebody is releasing it, it goes back and then compares this what I stored in the mutex data structure and what is there in the currently the CPU, which shows that the current CPU is currently the CPU is executing a process whose process ID is there in the CPU's register. So it will know immediately that it is not matching. So you are not allowed to release the mutex if because you are not the owner. So it can catch it. Mutex solves some of the problems encountered with the semaphore by bringing in discipline in the usage. So advantages of mutex: accidental release is not possible. Okay, if a process does not own a mutex, it cannot release. Who prevents it? OS prevents it. Okay, it doesn't do allow it to release it. It will return an error saying that you are not the owner. So recursive deadlock. Suppose the process itself calling again wait on the semaphore. It will not allow the process to wait if it is owning it already. So that deadlock is it will come out saying that you are the owner already. So you cannot call the sum wait on the same semaphore that you own already. So recursive deadlock is solved. OS can prevent it. Now, why should an error message be given? Because you can actually, based on the error, you can actually take some corrective action. By mistake, suppose in a user, suppose I told you the, occasion where you are interested in using two semaphores. Okay, wait on S1, then S2 you want to do. By mistake in your program, instead of S2, you call S1 again. Now, this is going to return an error, and your program, if it is checking for the error condition, it will land into some other area. Then you will realize, oh, this is the mistake I have made in the code, that instead of calling S2, I made it S1. So now I should correct it. So this is a mechanism, okay, where no S2 is the correct way of calling it. If I don't use S2 and if I use S1 again, it is going to cause a problem. Means it will return an error and you can actually correct your code. Okay, it is not going to function as normally. Process death deadlock. Now what happens? Suppose a process owns a semaphore and then it is exiting. Now remember, either pthread exit or exit is done. In both the cases, OS is aware the process is terminating. Please remember, process cannot do anything without the knowledge of the OS. Pthread exit is specific to the other family of processes which are there, or threads which are there. Whether they are aware of dying of a process or a thread is what is decided by whether the process is calling pthread exit or exit. Pthread exit will inform the entire family, whereas exit informs the OS. Both will inform the OS, of course, but exit will only inform the OS, but it will not. What it will do? It will just kill all the entire thing. Okay, all the family of threads which are there. If one executes exit, it will kill everybody because that's an illegal way of coming out of the exit. Okay, if you are calling pthread exit, you are saying informing the thread library that you are coming out. So the other processes can actually try to do a pthread join, and then it can actually do some action based on when the one of the threads in the family dies. Okay, so if the process death happens by owning it, any process death will anyway will be informed to the OS, and OS can check it. Are you owner of any of the currently busy semaphores? Okay, there can be a structure inside the PCB itself that which are the semaphores it is owning. See, remember, it's not going to go across the system to see all the semaphores that are there in the system currently and then whether this process is the owner of that. No, that is not the way it is implemented. When the process dies, it is whenever a process acquires a semaphore, that semaphore is ID is also stored in the PCB that it is owning it currently. So when the process dies, PCB is anyway is known based on the PID. Then it goes to the PCB and checks whether it does it own any semaphore. If it owns, now there is a possibility that after owning it is going to die. Without releasing it is the process is exiting. So we should take some corrective action. So what does the OS do? It knows the semaphore and goes to the semaphore's data structure and checks whether any processes are waiting on them. If it is waiting, some other processes are waiting on the semaphore. Now it has to take action because the waiting processes are waiting for the semaphore to be released, whereas the owner of the semaphore is going to exit now without properly executing the instruction pthread signal. Sem signal. Now OS is going to do the job of what the process should have done. It is going to wake up the process. with one of the processes, maybe not all of them, or it could implement it in such a way that all the processes waiting on that will be woken up with the same error saying that this particular semaphore was not released properly. It is in an unstable state. So all of you who are waiting for this semaphore, please take action accordingly. So that what action to be taken is not decided by the OS. It doesn't know what data you are protecting using the semaphore and what action is supposed to be done by you. What it is that job of the application to take care of it. Okay. So understand this now. Now, why should an error message be given? You can just freeze it and try to think about a reason for this. What could be the possible reason why error message should be sent to the processes which are waiting on a semaphore, which happen to have been not released by the owner, and the OS has done the job of releasing it because the process died without releasing the accidental death. Now that is the solution. Correct answer is C. Since the processes owning the mutex, the process, not processes, the process owning the mutex has died while inside the CS critical section. It could have left the critical section in an unstable state. All the waiting processes need to be informed so that they take any corrective action based on the application. It's not OS cannot do anything. Only thing what OS can do is, because it is aware, it can inform, and it is the responsibility of the application to take corrective action based on what they have implemented using the semaphore and what data they are manipulating. So now one more question, just freeze it and try to answer this. This is also very simple. Is once you know whether it is yes or no, you know that multiple character answer means two yes or two no. So think about it. Okay. Now B and D. That means what? We are no. Can a mutex be used to synchronize occurrences of an event? So I told you that you have a process, and then once can continue further right from there. Here, if you remember this, it is saying signal here and then wait here, right? Now these are operated by two different processes. It's not the same process. Now what if I do a signal, P1 is doing the signal, whereas it may be owning it, okay? But if I do this two different processes, one owning it and another process releasing it, which is going to cause some issue, okay? Sometimes we can even implement it that this is only is owning and then you are releasing it, but someone is waiting and they will be waking up. But the issue will be when you have the ownership of a semaphore. Sorry, we are not going to use the word semaphore. We are going to call it mutex. Then mutex has to be released by the person who is owning it. So if you allow two different processes to use it for releasing and acquiring it, is going to be an issue. So mutex is used only for critical section and not for synchronization. Okay, so that's what is told. Mutex is not used for synchronization because we want the unlocking and locking to be in pair, and it should be used by the same process who is owning it. Because if some other process is trying to do it, we are going to give a error saying that you are not the current owner, right? So and OS has no way of knowing actual use of mutex. So it is it is preferable or it is advisable to use only the mutexes for protecting the critical section and not for synchronization purpose. So it makes the implementation cleaner by not confusing the issue of mutual exclusion with the synchronization. So semaphores are used for synchronization as well as mutual exclusion, but it has a problem of erroneous call and deadlock, all these things. Whereas mutex is used for only mutual exclusion, and it cannot be used, or it should not be used for synchronization purpose, because we are taking action based on who is the owner. Based on that only, if the releasing is also controlled. So that's all about mutex. I hope it was useful to have a clear idea on mutex and what is the difference between mutex and semaphore. Now one more thing before we end this section: spin locks. Now I said that whenever a process comes to acquire a mutex or a semaphore, it is executing the wait, and if it sees that it is busy, that means somebody is already owning it and they are in critical section, it is going to be blocked. That means the running state process, because it has to be running to call this system call, right? So it is currently in running state now, because it has to be prevented from continuing further. That means it should be blocked. Then OS has to do a lot of job. What is that? It should change the state from running to blocked, and then it should also do a context switch and put it in PCB, then save all the context in the PCB, all the register contents, and then allow some other process to be scheduled using the scheduler. Now, what if I use the mutex? Okay, let me call it as mutex or semaphore, whatever it is, a binary one, only for a short duration. That means my critical section is too short that it may be just count plus plus or some simple operation, one few instructions, few cycles. Then any process owning it is going to release it immediately because I use the spin lock. Okay, I'm talking about spin lock now. I'm going to use the spin lock, which is uh, um, another way of implementing a binary semaphore. But here what I am doing is I'm not going to make the processes to be blocked. I want to really actually make the processes who is trying to acquire a semaphore to be in a busy, busy, busy wait. That means it is going to continuously check whether this semaphore is freed up or not. It is not similar to another variable, but it is the OS construct and it also needs a hardware support, and it is a semaphore wherein a wait function call does not put the process in the blocked state. It is actually continuously running and doing a busy wait on that particular semaphore to be released. Then when it is getting released, it will be continuously running checking, and then anybody owning it is likely to or expected to be releasing the spin lock immediately, and the waiting process will get a chance to run immediately. That means it will acquire it and then go inside. So spin lock is some mechanism where it is implemented in hardware. It should be supported by the CPU, and it is helpful for avoiding the processing delay from the OS perspective of blocking the process and context to see, putting removing the process from the CPU and bringing another process into the CPU. It continuously runs and checks for the spin lock to be released. The reason is spin locks are used only for critical sections which are very very short. Okay, it's not for very big database update or something. So this is what is mentioned here. Busy wait is done. It is spinning on the lock. That's why it's called spin lock. Okay, the process which is waiting on it, if it is already busy, it is going to spin lock it. But if it is free, it will immediately come down. Okay, and then get into the critical section. But it is supposed to exit from the critical section immediately, as early as possible. It should not take too much time. Okay, the reason is CPU other processes are going to be doing a busy wait on it, which is not good to have this spin lock to be protecting a longer critical section. Okay, so it is actually useful in a multi-core system. Okay, so once acquired, spin locks will usually be held until they are explicitly released, although in some implementation they may be automatically released if the thread being waited on blocks or goes to sleep. So one more way of preventing somebody acquires a spin lock and then goes into sleep, then the OS has an implementation in such a way that it can be released immediately. Okay, because anyway it is blocked and it is sleeping. So spin lock is meant for only short duration of protecting some data, so you can allow it to um, be released. Accidental release also can be prevented. Not accidental release is similar to process dying acquiring the semaphore. So spin lock is acquired, but it is going to sleep. Then OS will take care of releasing it automatically. So that's the spin lock. Now bounded buffer problem is a very popular one. It's a cyclic buffer where you have a common data buffer where you have multiple elements, and the producer task is trying to put some data into it, and the consumer task is taking away data from there. Now it is continuously running. It's a cyclic buffer. The data will be filled from top to bottom, and producer's job is to continuously produce it, and the consumer's job is to consume it continuously. Now, can we make sure that this particular implementation be done safely with the use of semaphores or mutex? Okay, so that's this problem is actually implemented in code, and that if you go through it will be clear, as well as I will try to explain it maybe in the next lecture. But understand that this bounded buffer problem is something like a cyclic buffer where data is put by the producer, and is two processes running continuously, and one guy puts the data and the other guy taking it out. So we need to have a common count to indicate how many data elements are there in the buffer, and then there should be a read pointer and write pointer where these producer and consumer are operating on. So of course, you from this context you will know that producer is going to use the write pointer, and then write pointer, if it goes to the end of the buffer, it should go back to 0. Similarly, consumer will be using the read pointer, and it will also be going to it. Count variable has to be there because you don't know number of elements which are there. Okay. Now when count is 0, what will happen? The consumer does not have any data to consume, so it will be blocked. And when the count is equal to the maximum number of elements in the buffer, then producer does not have space to put the data, so producer should be blocked. So that's how it should be implemented. And if you can freeze this video and look at the code, you will know that producer produces an item and checks whether it's already full. If it is full, it is going to sleep because there is no space to put the data, whatever you have created or produced. Now, once imagine that there is a possibility that it's not full, then you increment the count, which is very important because you have added a new element, so it should be incremented. And then it is doing one more thing which may be surprising to you. When count is equal to 1, it is waking up the consumer. The reason is when count is equal to 1, prior to this incrementing, that means what was the value of count prior to this? It was 0. And then you incremented to 1 and you check that it is equal to 1 now. That means that there is a possibility that a consumer process which is running could have been checking this, could have checked this count value, and it would have found out that count was 0 and it may be sleeping. Now who is going to wake it up? Unless the producer is waking it, does it, nobody else is going to wake up. OS is not going to come and say, hey, you wake up, your data has come. It's not his job. Okay, it cannot go across all the processes and see where the consumer is waiting. So it's very implementation specific, which OS does not come into the role at all. So it has to be done by the producer to the consumer. So this signaling can be done with the semaphore. Okay, mutex cannot be used, so I will use a semaphore here to do the signaling of sleeping guy. If it is not sleeping at all, no issues. You can knock the door. If nobody else is there, nobody is there in the house, no problem. Nobody is going to come and open the door. So if somebody is there, you want them to be open up. So that's what is done. Now similarly, when the consumer finds that after it consumes one data, it has become n-1. That means prior to my consumption, it was n. That means it was full. If that was full, maybe the possibility that producer could have checked it and found that it is n and sleeping. So in anticipation that maybe consumer is sleeping, you wake it up. Okay, this is the job of this waking up is nothing but synchronization, and semaphore will be used for this purpose. Okay, so I think this much of introduction about consumer and producer and the bounded buffer will be enough for you to even look at the code and understand the code. Now, what is the code does? Actually, this bounded buffer itself is implemented in the shared memory. Okay, because two processes are accessing. Remember, whenever two processes are accessing, I mentioned it even when there is a sync semaphore which is used by two different processes, that sync handle itself should be in a shared memory because that handle will not be known to both the processes unless it is put in a place where both will be knowing it. Both can have an access to it. Similarly, the buffer itself is accessed by both, so it should be in shared memory. And then the count should also be there, and other read and write pointer can be a part of this buffer itself. And producer and the consumer does the job of doing it, consuming it. Now, what should the count be? Count should be a common variable which is incremented by the producer and decremented by the consumer. That means it is accessed by both the processors, so it should be protected. So we need to have a mutex here to protect it. Okay, that mutex handle also should be part of this shared memory. If you understand this implementation that I am talking about, then if you look at the code of that current implementation, then you will be able to appreciate what is happening in the code. So this is how read and write pointers are there, and sleep call and wake up calls are purposes for this only. Okay, so I hope this is clear. Bye bye.